Everyone, today we are going to discuss the minimum weight subarray problem. In this question, what they are basically asking us that they have given us a source, they have given us two sources, source 1 and source 2, and a destination is given to us. They want us to create such a subarray which can include both sources, and at the end of the day, by traversing through both the sources, we are able to reach the destination within the minimum time. This is the question. We have to find such a subgraph which can give us the minimum distance, the minimum total weight of the edges, considering that it contains both zeros and ones and 5 at the end of the day. That is the destination. I myself struggled a bit with this question. If I have to show you, if you look at my submissions, you will realize that I got the wrong answer and the TLE a couple of times, and then I was able to solve this. So it's a good problem, I would say. Good problem to start with. I have provided the solution in here. I'll provide the link as well. So let's start off with the question. I'll quickly explain you. As I told you that we have to find that from two sources, how can we reach the destination in the minimum time span. Okay. So this question, if you look very closely to it, right, we have to figure out a LCA, a common node, which is in both 0 and 1. Both the sources, through both the sources, we have to find a LCA, which is like the common point for these two sources. Once we are able to find the common point, we want to figure out that from destination, how long will this LCA will take. And once we are clear with this, we have to just sum up from 0 to LCA, 1 to LCA, and LCA to destination. This will be a question at the end of the day, right? So at the end of the day, we have to figure out a common point from which we can say that now the graph is common. Before this, the graph was diverged. It can be different for source 1 and source 2. But by this point, if you go to destination, this will be the common point for both the subarrays or both the graphs. Okay. So which approach is coming to your mind when we say that we have to figure out an LCA? Now this LCA can be any node. From this 0, this LCA could be 1, 2, 3, 4, 5. We have to figure out the distance of 0, the distance of source 1 to all the subsequent subarrays, and we have to store it somewhere. Same thing we have to do with 1 as well. We have to find the distance of 1 with all the subarrays, and we have to store it somewhere. And then we have to consider each node as LCA, and then figure out that from destination, how each node will consume this destination. If this is my destination, I have to find the distance of all the node with this destination. Now at each point we have 3 array, right? We have 3 array at the end of the day. Each array will make sure that we have all the nodes distance stored, minimum distance stored based on the source 1. Second array will make sure that we have a source 1, source 2, which from the source 2, what is the distance through all the other nodes, or what is the minimum distance of this. If we consider each node, how much distance it will take to reach to 1. So it's basically the Dijkstra's that we are applying. And the third array stores that from the destination, what all points we can reach at the minimum distance. What is the shortest path, or what is the shortest distance from each node to my destination. So at the end of the day, once we are able to get these 3, we just have to figure out that, okay, sum these 3 up. Tell me the sum of these 3. Tell me what is the exact sum, and just return the minimum one. That will be our answer. So now you might ask that why this solution actually worked. We were able to find a LCA. We consider each node as an LCA. It's not like we consider this as an LCA or this as an LCA. No, we consider all the points as our LCAs. All the points as our LCAs. We calculated all the distance from source 1 to all the possible LCAs. We calculated all the distance of source 2 to all the possible LCAs that could be possible. And same we did for the destination. And in here, what we are doing, we are considering each node as a LCA, and we are figuring out, if we consider this ith index as my LCA, what is the minimum distance that I can get? What is the minimum distance of all the edges combined that I can get, and then I'm submitting that minimum value in my answer. Fine, this will be our approach. So what we have done, we have tried to find the shortest path. So we will discuss more about the shortest path in a few seconds. But let me tell you what we did. So when I'm saying I calculated all the nodes distance from my source 1, all the nodes distance from my source 2, and all the nodes distance from my destination. Correct? So when we talk about source 1, I'm easily able to figure out what is the shortest distance with each node. Correct? With each node I can see, okay, from 0 I can go to 2, from 2 I can go to 1. So the minimum distance that I can find from 0 to 1 is actually 3. Correct? And same for source 2 as well. But for destination it's a bit tricky. You see, in destination all the nodes are pointing to the destination. If you want to find that how much time it took for all the for destination to reach out to all the nodes, then it's not possible. Why? Because the nodes are actually not in the correct direction, right? So for destination, if we want to find all the distance with all the other nodes from this destination point, we have to use a reversed adjacent list. What reverse adjacent list means that the one, if we have u and v, if our edge is u to v, in the normal adjacency list we will write it as uv, we will write it as 0 and the value at edge 1. But for the reverse one, we will actually reverse it. We will pick the v first and then the u, where we are saying from v to u, this is the distance. So we have to consider a reverse adjacency list, and we have to pass the reverse adjacency list for this destination array, and not the adjacency list that we are passing from source 1 to all the array and source 2 to all the array. So that was a small trick over here. Now let's quickly discuss how do we actually calculate the shortest path from a particular node to all the other subsequent nodes. For this, the Dijistra's algorithm is known for, right? From Dijistra's algorithm, this is what we make sure that if we have a node and if we want to calculate the distance of this node from all the other nodes, that's where the Dijistra's comes in the picture, right? So what we have done, we have assigned a maximum value to our array. So if you know a bit about the Dijistra's, I'm not able to enter. Fine, the enter key is not working. So if you know a bit about Dijistra's, we assign infinite values to all the nodes. Okay, we consider all the nodes that they are infinitely distant from each other except the source one, because from source node, if you want to reach the source node, how much distance it will take? It will just take 0, right? Because I want to reach from my current position to my current position, that will be 0, right? So no matter what this source is, this source could be 1, this source could be 0, this source could be 5, whatever it is, just make sure that you assign 0 to it, which says that from here to here only you will require 0 energy or 0 weight, right? So maybe let's suppose I was talking for the source 2, right? So for that my source for that my distance is 0, perfect. But for all the other values it's infinite, max, if I have to put it that way. So for all the other values it's actually max, okay, something like this. Now what I'm doing, I have actually assigned this source comma 0 pair to my queue. So this is the pair that I'm using, which is making sure that I can have the weight and this vertex at the same time. It's very useful if you can declare a vertex. It could be different in your language, but this is how you do in Java. So once you have the pair with you, right, you can just go inside this while loop and you can continuously traverse over the entire queue until unless it's empty. And every time what we are doing, we are basically, this is the main logic of the Dijistra's algorithm, where we are taking all the adjacent node of this edge, correct? This is the way where we calculate the adjacent node. We have already assigned all the values inside our adjacency list. If you know this, we have already added all the subsequent values to the adjacency list, right? So now we will loop over all the edges that we have and we will check whatever value that you have currently here. If you take 0 and the distance of this source to this destination, if this is actually less than the original value that is present inside my array, that means this value could be replaced with this minimum value, correct? And then that's where we will update our array, and that's when we will assign a new value, or we will put a new value inside our queue, which will make sure that we are taking the vertex and the new weight that we just discovered. This weight is nothing but a smaller weight from which you can reach from source to this particular node 1, or from source to node 2. So this is a very classic Dijistra's algorithm. You can just loop over all the edges if the weight that we just got is making sure that you will now have a better weight than whatever it was there in the array previously. If this is making sure that you are smaller currently, if you consider this path, then just come inside this if loop, assign the new value and add that value inside the queue. And for queue also, we are actually using a priority queue. This makes sure that we are always picking up the minimum value first. So every time when we pop out of our queue, we are making sure we are picking up the minimum one, and through this minimum one, we are making sure that if I go to my adjacent point, or if I go to my neighbors, this is nothing but your neighbors. If I go to my neighbors with this minimum weight that I just discovered, will it be less? If it is less, then please consider me and add it to your queue. That's it. This is how you calculate the Dijistra's the shortest path from this node to all the other nodes using the Dijistra's. I have added some additional condition. This condition will help you to not give you TLE. If you can see, I was getting a TLE a few minutes ago. If I can show you, I was getting a TLE, right? So that's where this if condition helped me. This condition is saying that if the weight that is present in your array, correct, if the value that is present in your array is already less than the value that you just popped out of your queue, then you actually don't need to do it. You do not need to go inside the for loop, because anyways, no matter if you even come up with this weight, you will add something unnecessary to your queue at the end of the day. You will add something unnecessary to your queue at the end of the day, because we have figured out a better weight already. Our weight at this index is already less than what we are getting right now. Then there is no sense in considering that weight. This weight is just going to push some unnecessary data inside the queue, and it will loop over the queue again and again, and it will increase the time complexity at the end of the day. So if there is any confusion within the weight, just continue. Just do not go inside the for loop and add anything unnecessary inside the queue. So this condition is important for that perspective. So that's it. It was a good question. I was not able to find many good solution on the internet, so I thought maybe I can push this code. I know I did it a bit fast, but let me know if you need any help. The question is very easy. Not easy, I would say, but the question is very interesting. This will help you to get a very better understanding of the Dijistra's algorithm. If there is one question that I would suggest everyone to solve if they want to have a better understanding of Dijistra's, this is definitely the question. What we are doing, we are calculating all the subsequent distances from source to all the other nodes, from source 2 to all the other nodes, and from destination in the reverse order to all the other nodes. And once we got all the arrays with us, we will consider each node as our LCA, and this I index denotes nothing but LCA at every point. And with each LCA, we will see, okay, I'm considering this point as my middle point, or as my common point. Now tell me how much distance from 1 it will take to reach 2, how much distance it will take from 0 to reach 2, and how much distance it will take from 5 to reach 2. And all three of them will give me a weight, and I'll sum all the weights up, and I'll say, okay, this, if I consider 2 as my LCA, this is the distance I'm getting, this is the distance I'm getting, and so on. And there will be a point when I'll get a minimum point, and I'll return out of it. There is one extra condition that I have written. This is very, very common. You know, when will we get a long of max value? If you see, we have filled our array with long of max value initially at the very start, right? So this actually means that we were not able to assign anything to our array list. Basically, this node was never reachable. We were never able to assign a better value to this point, right? So if a point is not reachable, that means we were not able to reach that point, right? And here it is very clear that if a subarray does not exist, basically if you're not able to reach this point, then there is no sense in saying that, okay, 3 is LCA. Why we can't say 3 is LCA? Because we can't reach to 3 from 5 or from 1 or whatever it is. So in this condition, if there is any point for which any of these 3 points are not reachable, then there is no sense in calculating minimum for them, right? We will just continue out of it. And the last point is this: if at the end of the day none of them were able to update my minimum was this and it was always this, if that's the condition, then we will return -1, seeing that there is no subgraph that exists, else we'll return the minimum one. So that's all. This is the solution. I'll provide you the solution as well. Let me know in the comment section if you have any doubt. This is a very good question. Try it out. It uses your priority queue, your digistras, your skills to create adjacency list, reverse an adjacency list, your skills to figure out if you actually have to consider this as your minimum value or not. So this is a very good question. Just go through it and let me know if you have any question. Okay, thank you so much.